Right, 7L angular momentum. There's a planet orbits a star in the counterclockwise orbit shown in the diagram at right. The planet is at point A, and then later that same year, it's at point B, and later that same year, it's at point C. We're going to call that time capital T. The kinetic energy of the planet is shown on the graph below. That's the black line. Total energy of the star-planet system is shown on the same grid by the dashed line as a function of time. So basically, the kinetic energy is the black line. So what we're seeing there is that the kinetic energy gets bigger, then goes to a minimum, and then gets bigger, and then goes to a minimum. And what are we supposed to do? Nothing yet. I guess we're going to draw on the graph later. Suppose it takes 1.25 Earth years for the planet to travel from A to B. How many years are shown on the graph above? So how many years? Well, that's a half of a year for whatever this planet is. From A to B, it's half of its year. It takes 1.25 years to go from A to B. So how many? And so I'm looking at 2 cycles in the graph. So basically, the pointy part of the graph here, that's showing me that I'm at point B, because that's where I'm going to be going the fastest, when I'm closest to the sun. So I'm at point B here, and I'm at point B here. So from this point to this point, I've gone all the way around the ellipse, right? And so that would be 2.5 years. So it shows from point A to B is half an orbit, so a full orbit is 2.5 years. So the graph shows 2 full orbits. Okay, so it's starting here at A, and then it's going to B, then it's at A, then it's at B, then it's at A. So we started at A, and we went to A, then we went to A. Right, so 5 years of Earth time. Half of 1.25 years is 0.625 years. Does it take 0.625 years for the planet to go from B to point C? Explain your reasoning. Well, here's the thing. See, it's changing its speed. So if it were going at a constant speed, then yeah, it would take half the time to go half the way. But it's actually going much faster from B to C than it is going from C to A. So I'm going to say no. It doesn't take half of a half year. It's going to take less than that. And that's what they're going to say too. And you're welcome to read these red words, because yay. On the graph above, sketch the graph of the potential energy. So that's what they've done there. So they went back over here, and wherever the kinetic energy is a maximum, then the potential energy is going to be a minimum. So you can see here, we're starting off with high potential energy, and then low. And so see how it's always negative also? Here's 0. We're below the line here. So we're at negative potential energy, then it gets more negative, then it gets less negative, then it gets more negative, then it gets less negative. That's our convention for potential energy due to gravity, is that it's negative. And when it's less negative, it's bigger. Oof. Draw a vector labeled V representing the velocity of the planet at point C, and label a vector labeled F representing the net force exerted on the planet at point C. Well, let's go back over here. So the velocity is a tangential velocity, right? If this planet were attached to the sun by a string that was going around in this ellipse, and we cut the string, the planet would just go sailing off into outer space at this tangential direction. And then the inward force is centripetal force. It's going in a circular type of path, so we get a centripetal inward force. That's why those look the way they do. All right, part C, part D, part E. At time TT, when the planet is at point C, the kinetic energy is decreasing. Use your vectors drawn in part D to explain why this is the case. Well, I don't know about using your vectors drawn to explain why this is the case. What I would say is, As it gets farther away from the planet, its potential energy increases, so its speed has to decrease to keep the energy, this total energy, the same. And there's nothing in this cup. That's a bummer. Sketch a graph of the angular momentum of the planet. Well, it's just going to be constant because there's not an external force acting on the planet star system. There's no net torque, so the angular momentum will stay the same. Massive pulley. Oh, this is a fun, well, I don't know about fun, but this is a lab that we have done in class once. And you have this pulley, you have a mass, and you can wrap this rope around the axle, and so that it kind of unrolls. And as it unrolls, it gives a speed graph. You can see that it's got this concave, hyperbolic type of curve, right? Or it's actually the speed is slowing down as it unrolls. Why is that? Write an equation that represents Newton's second law as applied to the mass, then use it to equation to estimate the tensions in the string. So we have F equals ma, gravity and tension equals ma, the acceleration is the slope is 0.8, the slope is 0.3, depending on where we're at in two different places. So at the beginning it's 0.8, at the end it's 0.3, approximately. So we use the mg minus the so they're using the slope for ma, right? So the tension is equal to force of gravity minus ma. They just did rearrange the second line of the here. They said, well, let's just set tension equal to the other two things. So at the beginning, the slope is steeper, so the a is 0.8, and if you just crunch the numbers, you get 18 newtons. And at the end, the slope is shallower, and then you crunch the numbers and you get 19 newtons. So here's some words that explain what we're doing mathematically. And so basically what you're getting is a greater tension in the rope. As the rope unwinds, the tension increases. So this is, remember before when we were doing pulleys and we had objects going on pulleys, we always pretended like the mass of the pulley didn't matter. Well, when we study rotational motion, it's not actually true. So what we're seeing here is that the mass of the pulley does matter because the pulley having a mass gives it a moment of inertia. And that moment of inertia motion is going to affect the system. And so as the pulley rotates, the tension actually doesn't stay. So in the old, when we did Atwood machine problems, the tension, we always assumed the tension was the same all the time. It was constant, and it was the same on both sides of the Atwood machine. But if the pulley actually has mass and it has a moment of inertia, then it's not true. The tension changes as the system changes. The radius of the rope decreases, exerting less torque on the axle, smaller torque, less rotation. And that's why the acceleration decreases. That's crazy. Mr. Burkhart has a bicycle tire just like this in his classroom. And so now we can be sad one more time that we don't get to play with this bicycle tire in Mr. Burkhart's classroom. So this is you explain how Angela does it. So this is basically you write up a lab for Angela so that she can do what? Finding the torque that's applied to the wheel by the force of friction. So here you go. You can see how Angela could do it. Maybe you could think of a different way to do it. Let me just read through this and see if there's anything that I need to explain to you what it is. So we know what meter sticks are and what strings are. Force sensor, you can imagine basically it's a magic box with electronics in it, and you hook it up to a meter, and it'll tell you how hard things are being pulled, and it just reads it out digitally, right? So you don't really need to have any sort of sense. It's basically a box with a hook on it, and inside there are magic electronic circuits, which will convert the tension on the hook into a force reading on the sensor. All right, computer program, and use a motion detector. Same thing. It's a magic box. It sends out ultrasonic signals that bounce off the object, and they bounce back just like a bat that hears, or a radar gun that the police use. It tells you how fast something's moving. Motion sensor. Repeat for accuracy. You can always say that. You might get a point. Okay. And she could place a piece of tape on the wheel as a marker. Use a photo gate. So I think we've seen some of this stuff, at least in videos that Burkhardt did. We've seen the photo gate timer, I'm sure. So the photo gate, when you break it's a little red light that goes across a gap, and when you break the light, it hits a trigger on the timer. And LMNO. Okay, so we're almost done. And so here is how Angela could calculate the rotational inertia of the wheel. And you're welcome to read through this and ask me questions about it. And now we're on the last section. And I'm getting hungry. I gotta stop doing this. Go. So it's not uniform in its density. So I actually have a little bird that I can balance on my finger. I can put the beak of the bird on my finger. It's not a real bird. It's a plastic bird, and it's a trick bird. They've constructed so that it has a weird center of gravity. So this bar has a weird center of gravity, and they can balance it on their finger, not in the middle, because it's not equal. It's not equal density. Okay. Blake could follow to take measurements to calculate the rotational inertia. All right, and so what you need to do is you need to take some measurements for the rotational inertia of the bar. That's its moment of inertia. That's just a different way of saying moment of inertia. And so we could try to figure out its angular its angular speed. We can measure the torque. We can measure the force and the radius. There's different things we can measure to calculate I. And you can read this. Pause the video. All right, and we are not going to be doing Unit 8. Not out of this workbook. Yeehaw!